everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to see a few basic terms that are involved in fiber optics. So in our previous lectures, we have seen the principal construction and working of optical fiber, and today we'll be mainly focusing on acceptance angle, numerical aperture and critical angle. Now let us have a brief outline of the topic for discussion today. First we'll see the recap of the working principle, because it is very important to understand the working principle in order to understand these terms. So we'll be seeing the definitions for critical angle, acceptance angle and numerical aperture, and later on we'll be deriving the expressions for all the three: critical angle, acceptance angle and numerical aperture. So if we come to the introduction to fiber optics, optical fiber is a flexible, transparent fiber made of extruded glass, that is silica or plastic, which is slightly thicker than a human hair. It can function as a waveguide or light pipe to transmit light between the two ends of the fiber. So when light travels through the optical fiber, this optical fiber acts as a waveguide, means it guides the wave, or we can also call it as a light pipe, because through that pipe the light travels, which carries the signal. Power over fiber, which we call them as POF, optical cables, can also work to deliver an electric current for low power electrical devices. So these optical cables, especially POF cables, they can be used to carry the electric current for low power electric devices. Now optical fibers, they are widely used in fiber optic communications, wide applications in communications, where they permit transmission over long distances and at higher bandwidths than the wire cables. So when we compare the bandwidth of an optical fiber with that of an ordinary cable, that is a metal wire that carries the signals, the bandwidth here means the range of frequencies that it can carry is very large when compared to the conventional cables. So fibers are used instead of metal wires because signals travel along them with less loss, and they're also immune to electromagnetic interference. So electromagnetic interference here represents to the disturbance that is caused due to electromagnetic radiation. Because of these disturbances, there may be loss of signal. But when we take optical fiber, they are immune to these losses. So there will be less loss of the signal. And also fiber optical fibers can also be used for illumination, that is illuminating purposes or decorating purposes. And they are wrapped in bundles so that they may be able to carry the images. Now coming to the structure of optical fiber, it consists of three main parts. We see different sections of optical fiber, but we always talk about three main parts: the core, cladding and the coating, or the buffer or outer jacket we may call it. So what is a core? A core is a cylindrical rod of dielectric material. We are taking a cylindrical rod of a dielectric material, and light propagates mainly along the core of the fiber. So it is the core that carries the signal with the help of light, and the core is generally made up of glass. The core is described as having an index of refraction N1, or we may also call it as refractive index. So generally what we represent here is the refractive index of the core is represented by N1 and the diameter of the core is 10 to 100 micrometer. Micro means 10 power minus 6. So the diameter ranges from 10 into 10 power minus 6 to 100 into 10 power minus 6. So 10 power minus 6 meter is 1 micrometer. Now coming to the next one, that is cladding. A core is surrounded by a layer of material called cladding, which is generally made up of glass or plastic. We have seen that the core is made up of glass. Now when we are talking about cladding, the cladding is surrounding the core and it is made up of either glass or plastic. And the cladding layer is also made up of dielectric material whose refractive index is N2. So for core it is N1 and for cladding the refractive index is N2. Now what we consider here always is the index of refraction of the cladding is less than that of the core. In other words, I can put it as N1 should be always greater than N2. Means the refractive index of the core should always be greater than the refractive index of the cladding. When we talk about the working principle, we are going to discuss why the refractive index of the core should be greater than the refractive index of the cladding. And the diameter of the cladding is usually 100 to 200 micrometer. Again here, it is ranging from 100 to 200 micrometer. Now, after the cladding, we have silicon coating. If we see in the diagram here, the first part, this is what we are calling it as the core, which is made up of glass usually or silica. This is the core. So the outer covering for the core is the cladding. It may be made of either glass or plastic. Now covering this cladding, we have the silicon coating. This is the silicon coating. And this silicon coating is provided between the buffer jacket and the cladding. So if you see, this is the buffer jacket and this is the cladding. So the silicon coating lies in between the cladding and the buffer jacket and its main function is to improve the quality of transmission of light. So what we are talking about here is the silicon coating whose main function is to improve the quality of transmission of light. Then we have the buffer jacket. Silicon coating is surrounded by buffer jacket. So after the silicon coating, we are having the buffer jacket and it is made up of plastic that protects the fiber cable from moisture. So the main function of the buffer jacket is protection, protecting the fiber against the moisture. Next comes the strength member. The buffer jacket is surrounded by a strength member and as the name suggests, it provides strength to the fiber cable. So if you see here, the first part we had is the core. Then after the core, we have the cladding. And the third one is the silicon coating. So after the silicon coating, we have the buffer jacket. And now we are talking about the strength member, which provides strength to the fiber. And after the strength member, we have an outer jacket, which we call it as a black polyurethane outer jacket. So finally, the fiber cable is covered by polyurethane outer jacket. And because of this arrangement, fiber cable will not be damaged because we have seen the functions of each. Core carries the signal, cladding provides a support and it also supports the necessary condition that is required for the working principle. Then we have the silicon coating, then the buffer jacket, which gives strength to the material, and also we have a strength material and a polyurethane outer jacket. So because of this, what happens? It is protected against the damage during pulling, bending, stretching and rolling through the fiber because it is made up of glasses. So whenever we are using these optical fibers, it may be required to pull long wires, and also when we are laying these optical fiber for communication purposes, you may have to bend it or stretch it. So during all these processes, it should not get damaged. So we are taking care regarding this during the construction of the optical fiber. Now coming to the characteristics of optical fiber, they are very small in size and are light in weight when compared to electrical cables. Electrical cables, here we are talking about the metal wires. So they are very small in size and light in weight when compared to the electrical cables. And also they are flexible and have very high tensile strength. Tensile strength here represents the load that it can bear before breaking. So when we are using an optical fiber, they should be flexible and also they should have high tensile strength. So because of these properties, they can be twisted and bent very easily. And optical fiber communication is free from electromagnetic interference. We have already seen that because of this fiber it is immune to electromagnetic interference. So there will be less loss of signal. Then fiber optics do not carry high voltage or current. So they are safer than electrical cables. So whenever we are using optical fibers, they are carrying or operated at a very low voltage or currents. Therefore, it is very safe. And in optical fiber system, the transmission losses are as low as 0.1 dB per kilometer. So if you are talking about 1 kilometer of the wire, the transmission loss is only 0.1 dB. And also optical fibers have greater information carrying capacity due to greater bandwidth. So through one optical fiber, we can send a large amount of information. And in many cases, what we do is we can use one single optical fiber to send many signals. So it is also important to understand how many signals can be sent through one optical fiber because it has a large bandwidth. So different type of signals, you can divide them into bands, and each type of signal can be sent at a different frequency. So you can send telex, fax, telecommunication, all the signals, internet, all signals can be sent through one optical fiber. That is very important for optical fibers. Now coming to the principle of optical fiber. Optical fiber carries light from one end to the other end by the principle of total internal reflection. In a short form, you may also call it as T.I.R. So T.I.R. stands for total internal reflection. And there are three properties that affect total internal reflection. So we are going to discuss very briefly about these three properties. The first one is reflection. What is reflection here? When you have a surface, a polished surface, and light is incident on this surface, and because it's a polished surface, light cannot transmit to the surface through the surface, but it gets reflected. So when I draw a normal here, this is the incident ray, this is the angle of incidence, this is the reflected ray. So the ray that comes, the incident ray, is incident on the surface and it is getting reflected back into the same medium. So this is the reflected ray. This is angle R. And we also know the laws of reflection. Angle I is always equal to angle R. So this is what we see in reflection. Now coming to refractive index. So when we talk about refractive index, we need to know about the material through which the light is passing, because light, as long as it travels through the same medium, it travels in straight lines. But whenever there is a change in medium, the speed of light varies. So refractive index is defined as the ratio of the velocity of light to the velocity of light in that particular medium. So we are going to define the refractive index and denote it by n. So n is equal to c upon v. So c here represents the velocity of light. And v represents the velocity of light in that medium, whatever medium it is traveling through. So we are going to find the velocity of light in that particular medium. So what we understand here is, if the velocity of light is more, means the refractive index is less. So through materials whose refractive index is low, the velocity is high. And then coming to refraction. Refraction is nothing but bending of the light ray at the surface of separation of two different media. So now we have seen, because of the change in media, depending upon the refractive index of the media, the velocity will change. So when velocity varies, there will be bending in the light ray. So what we see here in refraction is, if you have a surface, we'll draw a normal here. Suppose we take one medium which is rarer and the other which is denser. These two are relative terms. One medium whose refractive index is less, we call it as a rarer medium, and the one whose refractive index is high, we call it as denser medium. So if a ray of light is incident on this surface at an angle I, angle I here is the angle of incidence which the incident ray makes with the normal. Now because it is changing the medium, when it is able to transmit through the other surface, its velocity varies. So because of that, it bends towards the normal. Because it is coming from rarer to denser medium, the ray of light bends towards the normal. So if you see here, the angle of incidence is always greater than the angle of refraction. So angle I is greater than angle R. Now if we see the other case in the sense, if it comes from a denser medium to a rarer medium, means if the ray of light comes from a denser medium, this is the angle of incidence, this is the incident ray. Because it is coming from denser to rarer, so when it is going to a rarer medium whose refractive index is less than the denser medium, then it may travel fast, so it may bend away from the normal. So we call this is R. And here if you see, angle I is less than angle R. So these are the two things we need to understand or remember regarding refraction. So whenever there is a change in medium, there is a bending of the light ray. And when it comes from rarer to denser, it bends towards the normal. And when it comes from denser to rarer, it bends away from the normal. Now coming to the phenomena, when we try to understand the phenomena of total internal reflection, what we see here is, when the angle of incidence increases, the angle of refraction also increases. We have seen two different cases. Now what we are going to do is, we are going to vary the angle of incidence. The angle of incidence means the angle which the incident ray makes with the normal. So if we see here, this is one medium which is a denser medium and this is a rarer medium. So we are going to consider the second case where a ray of light is coming from denser medium to rarer medium. So this ray is now incident on the surface. This is the incident ray. This is the normal. And the angle which the incident ray makes with the normal, here we are showing by theta 1. So as we have understood now, when it comes from denser to rarer, instead of going straight like this, it bends away from the normal. and this is angle R. Suppose if theta 1 increases, the angle of refraction also increases. So what is happening here is, as we increase this angle of refraction also increases and the ray bends away from the normal. As it bends away from normal, at one particular point or at one particular angle of incidence, this ray grazes the surface, touches the surface. Means it is bending away and away from the normal and it is now coming and touching the surface. So this particular angle of incidence at which the refracted ray grazes the surface, we call it as critical angle. And at this position, at critical angle, the angle of refraction is 90 degree. So what we are trying to understand, as the angle of incidence increases, the angle of refraction also increases. And then a stage is reached when the refracted ray just grazes the surface. So what is the angle at which it grazes the surface? At critical angle. And at critical angle, what is the angle of refraction? It is 90 degree. Now, let us define what is critical angle. The angle of incidence is called the critical angle of the denser medium with respect to the rarer medium. Means the angle of incidence at which the angle of refraction is 90 degree, we call it as a critical angle. And as the angle of incidence is increased, the ray is totally reflected. Means even after achieving critical angle, so this is the critical angle at which the angle of refraction is 90. Means if this is the ray that is incident, this is the ray that is refracted. So the angle of refraction is 90. Now, even after theta c, if the ray is incident at an angle greater than critical angle, so definitely the angle of refraction has to be more than 90, because as the angle of incidence increases, the angle of refraction also increases. So if I is greater than theta c, then R has to be more than 90, means the ray will get reflected back into the same medium. So we are calling it as totally reflected, and we are calling it as this phenomenon as total internal reflection. Now let us understand the entire phenomenon of total internal reflection. What we are talking about is, as the angle of incidence increases, the angle of refraction also increases. And if the angle of refraction is 90 in the rarer medium, then the corresponding angle of incidence in the denser medium, we are calling it as critical angle. So when a light ray is traveling in the denser medium, if the angle of incidence is larger than critical angle, we have seen the condition when I is greater than theta c, then the light ray does not enter into the rarer medium, but it comes back into the denser medium, and we are calling it as total internal reflection. So here if you see in the diagram, the ray of light is going from denser to rarer medium, and the angle at which it is incident, I, is greater than theta c, that is the critical angle. So what is happening here is the ray gets reflected back into the same medium, which we are calling it as total internal reflection. So what is happening here is the light ray does not get absorbed or transmitted or refracted from the interface, but it always gets reflected back to the denser medium. That is what we see in total internal reflection. Now, let us understand the conditions that are required for total internal reflection. So, there are two conditions that are to be satisfied for total internal reflection. So, the first one we have seen, the ray of light should always come from a denser medium to a rarer medium. The first condition is it should always come from a denser medium to a rarer medium. And the second thing is the angle of incidence should be greater than the critical angle. So these are the two conditions that are to be satisfied for total internal reflection to occur. Now, how do we apply it in an optical fiber? So when we have seen the construction of the optical fiber, we have seen three main parts, and in that two are very important, the core and the cladding. So we try to select that the refractive index of the core N1 should be slightly greater than that of the cladding. So the first condition will be satisfied because the light enters the core and then it touches the surface of the core and cladding. Then what happens here, if you are keeping the refractive index of the core greater than the cladding, the first condition, that is the ray of light should come from a denser medium to a rarer medium, will be satisfied. And the second condition, the angle of incidence at the core cladding interface should be greater than the critical angle. So we can calculate the critical angle for those two particular refractive indices. The refractive index of the core denoted by N1 and the refractive index of the cladding denoted by N2. So for these materials, we can calculate the critical angle, and if the angle of incidence is greater than that critical angle, so definitely there will be total internal reflection. So when we see the working principle of optical fiber, it is based on total internal reflection. And for total internal reflection to occur through an optical fiber, these two conditions are very important. The refractive index of the core should be greater than the refractive index of the cladding, and the angle at which the light is incident at the interface of core and cladding, it should be greater than the critical angle. Now let us see how it is the light ray is passing through the optical fiber. So when a light ray traveling from an optically denser medium to a rarer medium, it is incident at an angle greater than the critical angle, then the ray is totally reflected back into the same medium by obeying the laws of reflection. And this phenomena we are calling it as total internal reflection. Suppose this is the light ray that is incident. Now this is the core. The red part what we see here is this is the core, and this is the cladding. The black one which we are saying, this is the cladding. Now when a ray of light is incident here at the interface, and if it is incident at an angle greater than the critical angle, then what happens? It reflects back into the same medium. Again, the same thing happens here, it reflects back. Like that, there will be multiple reflections, which we are calling it as total internal reflection. Now the principle of optical fiber. This effect is used in optical fibers to confine the light in the core. So if it is not totally internal reflected, what happens? Some amount of light may get transmitted through the cladding, then there may be loss of signal. So to confine the light, to make the light travel only through the core, this following the principle of total internal reflection is very important. So what happens here is light travels through the fiber core, bouncing back and forth between the core and the cladding. So it will only bounce back inside the core, means it will be bouncing back at the interface of the core and cladding, and it will pass only through the core. Because the light must strike the boundary with an angle greater than the critical angle, only light that enters the fiber within a certain range of angles can travel through the fiber without leaking out. That is what we are talking about, the condition of I greater than theta c. So only those light rays that are striking the boundary at an angle I greater than theta c are able to travel through the core, and the rest of the things are leaked out. Now let us derive an expression for the critical angle. We have considered the refractive indices of the core, refractive indices I can write here, of the core and cladding as N1 and N2. N1 for core and N2 for cladding. So according to the law of refraction, N1 sin theta 1 should be equal to N2 sin theta. So what we consider here is two different medium. So this is the denser medium. Here we are calling it as core, whose refractive index is N1. It is coming from denser to rarer medium. This is the cladding, whose refractive index is N2. Now a ray of light is incident here at the interface. This angle is theta1. So because it is coming from denser to rarer medium, it bends away from the normal. This is the refracted ray and this is the angle of refraction. So how do we write using the law of refraction? N1 sine theta 1 is equal to N2 sine theta 2, or we have N1 by N2 is equal to sine theta 1 by sine theta 2 by sine theta 1. Now we will apply the conditions. In case this angle theta 1 is equal to theta c. So if theta 1 is equal to theta c, then what happens at this particular angle of incidence? This refracted ray just grazes the surface. Means the angle of refraction is equal to 90. What is the angle of refraction here we are talking about is theta 2. So theta 2 is equal to 90. So we will put these two conditions. Theta 1 is equal to theta c and theta 2 is equal to 90. So if you substitute in the equation 1, this is equation 1. So N1 sine theta c is equal to N2 sine 90. After substituting these two conditions, when theta 1 is equal to theta c, theta 2 will be equal to 90. We are putting these two conditions here. So we have sine theta c is equal to N2 by N1 because we know sine 90 is equal to 1. Since sine 90 degree is equal to 1. So what we have, we are writing the formula for theta c. So sine theta c is equal to N2 upon N1 and we have to write for theta c, it will become sine inverse of N2 by N1. So that is how we calculate the critical angle. So now the critical angle depends upon the refractive indices of the two materials. So N1 the refractive index of the core and N2 the refractive index of the cladding. So for a given material, the refractive index is fixed. So whatever materials we are using for core and cladding, if we know the refractive indices, we can find the critical angle. And if we can make the light to be incident at an angle greater than this angle, critical angle, then we can get total internal reflection. So this is the expression for total internal reflection. So in case of total internal reflection, there is absolutely no absorption of light energy at the reflecting surface. This is one point which we have to remember. No absorption or no loss of signal. Now coming to the acceptance angle. So what is acceptance angle? It is angle at which the beam has to be launched at one of its ends in order to enable the entire light to propagate through the fiber. So we are talking about the fiber. So if you see, this is the optical fiber where we are representing only two parts. Even though it has many parts we have seen, we are representing only two parts. The first one is the core. This is the core. You can see this is the core. And this is the cladding. This is the cladding. Now we are talking about the acceptance angle. So it is the angle at which the beam has to be launched. Means the angle at which the light has to be incident. Like this. At one of its ends in order to enable the entire light to propagate through the fiber means it has to undergo total internal reflection inside the core and pass through. So what should be the angle at which it has to be incident so that the entire light can propagate through the fiber? We are calling it as acceptance angle. So how we are going to measure it, we are seeing now. So it can also be defined as the maximum angle of incidence at the end of the optical fiber. Both mean the same, we are writing it in other words. So the maximum angle at which it has to be incident for which the ray can propagate through the core material. The same diagram we are writing in terms of the maximum. It is the maximum angle. If the angle of incidence is greater than that, So the light may not propagate through the fiber. There may be loss of light. Now coming to the acceptance cone. So acceptance cone here is the cone that is obtained by rotating a ray at the end face of the optical fiber around the fiber axis with an acceptance angle. We have already defined the acceptance angle, means the angle at which it has to be made incident so that the entire light can propagate through the fiber. Now how do we get this acceptance cone? If we take a light ray, say this is the ray that is incident. If you take this ray and rotate it about the axis, this is the axis of the optical fiber. This is the axis of the optical fiber. So how do we get this cone? We will try to understand. You take this ray and rotate it around the axis, fiber axis, with the acceptance angle. Then we get the acceptance cone. And light that is launched within this acceptance cone alone will be accepted and propagated to the other end of the fiber by total internal reflection. So that is the importance of the acceptance cone. Till now we are talking in terms of angle. Angle means the angle at which it has to be incident, maximum angle, so that the light can propagate through the optical fiber. Now we are talking about the entire range of angles at which it can be incident so that it can propagate. So how do we get that? We can define it with the help of the acceptance cone. So when we are taking a light ray that is incident, rotate it about the axis, we get a cone, and all the rays that are incident at angles which fall inside the cone, they alone can propagate through the optical fiber, and the other things we cannot go through the fiber. So if you have larger acceptance angles, means a larger cone, and it makes the launching easier. Means to launch the light inside the optical fiber is also a very important thing. So when you have larger acceptance cone, how do we get larger acceptance cone if the acceptance angle is larger? So larger acceptance angles make launching easier. Launching here means launching of the signal. If the signal has to propagate through the optical fiber, it has to be incident at a particular angle which we are calling as acceptance angle. So larger acceptance angles make launching easier. Now let us understand this diagram to calculate the acceptance angle. We are going to derive an expression for acceptance angle. So what we see here is, this is the core. Okay. Core is surrounded by cladding. This is the cladding material on both the sides. Here we are only showing the two-dimensional. If you see in the three-dimensional view, you have a cylindrical rod of core and the cladding will be surrounding the core. Now, when we are talking about core, the refractive index of the core is N1 and the refractive index of cladding is N2. We have also discussed about the acceptance angle, the maximum angle at which it has to be incident for light to propagate through the fiber. And this is the fiber axis, the central line that passes through the optical fiber. We are calling it as the fiber axis. Now, if this is the ray of light that is incident, if you rotate it along the axis, we are getting the cone. This is the cone. Means I can say this is the entire cone. Now, when the light ray is incident here, this light ray comes from air, suppose, whose refractive index is N0. It is incident here, say at an angle theta naught. Now, when the light ray is coming from one medium to another medium, it is coming from air. This is the interface at which it is launched. Now it bends towards the normal because it is coming from air to core. Core is generally made up of glass, we said. So whenever it comes from a rarer medium to a denser medium, it bends towards the normal. So this is the angle of refraction. So incident at theta naught and this is theta 1. Now this light ray, when it is incident here at the interface of the cladding, this is the cladding and this is the core. This is the interface of core cladding. Now at a particular angle which we call as the critical angle, we have seen that the angle of refraction is equal to 90. Now if this angle is theta, this angle is also theta 1. This is theta 1. So this is also theta 1 because this is like a transversal between two parallel rays. So if this is theta 1, we can write this as 90 minus theta 1 because this is a right angle. This is theta 1. So this angle will be 90 minus theta 1. So this becomes the angle of incidence here and this is the angle of refraction. So with this we will move forward to derive the expression. So for light rays to propagate through the fiber by total internal reflection, they have to be incident within the angle which is called as the acceptance angle. So this we have already understood. Now we will try to apply Snell's law. Snell's law at B. We have also discussed Snell's law. The ratio of the sine of the angle of incidence to the sine of angle of refraction is always a constant. We have also seen this with the help of two different refractive indices. So applying Snell's law at B. B is this point. We will apply the Snell's law. So at the Snell's law, what we try to understand, the refractive index here for the core is N1, means it is coming from a material whose refractive index is N1. This is the interface. What is the angle at which it is incident? This is the angle of incidence, that is 90 minus theta 1. And what is the angle of refraction? It is 90. And the refractive index here is N2. So how do we write Snell's law? N1 sine 90 minus theta 1 means the refractive index multiplied by the angle at which it is incident, that is 90 minus theta 1, is equal to N2 sine 90. N2 is the refractive index. N2 is the refractive index and the angle is 90. So we are writing it as N1 sine 90 minus theta 1 is equal to N2 sine 90. Now what is sine 90 minus theta 1? If you see the trigonometric functions, so sine 90 becomes cos. So we'll write it as N1 cos theta 1 is equal to N2 because since sine 90 degree is equal to 1. So what we have here is N1 cos theta 1 is equal to N2. So if we have to write for cos theta 1, we'll do the transposition. N1 will come to the denominator. So cos theta 1 is equal to N2 upon N1. And from here we'll write the formula for sine theta. We know sine square theta plus cos square theta is equal to 1. So if we have to write the formula for sine square theta, it will be 1 minus cos square theta. So from here we can write the formula for sine theta. So sine theta will be equal to under root 1 minus cos square theta. So sine theta is equal to 1 minus cos square theta power half. Instead of writing root, we are writing it as power half. And now we have also derived the expression for cos theta. Cos theta 1 is equal to N2 by N1. Mere substitution here. For cos square theta, we'll write N2 square by N1 square. Cos theta is N2 by N1. So cos square theta will be N2 square upon N1 square. So we are writing 1 minus N2 square by N1 square. Whole thing is power half. So this is the formula we have now for sine theta 1. Now we'll try to apply the Snell's law at O. So when you apply it at O, what happens? N naught sine theta naught will be equal to N1 sine theta 1. And sine theta naught will be, you will take N naught onto the other side, N1 by N naught sine theta 1. So what we are discussing here is at O. At this point, we have seen that the refractive index is N naught and the angle at which it is incident is theta naught. The angle of refraction is theta 1 and the refractive index is N1. So from this figure at the point O, what we can write is n naught sine theta naught will be equal to n1 sine theta 1. This is the point O we are talking about. This is nothing but Snell's law. We are applying the Snell's law at the point O. So n naught sine theta naught is equal to n1 sine theta 1. Now sine theta naught is equal to n1 by n naught into sine theta 1. We are going to substitute equation 1 into. What is our equation 1? Writing for sine theta 1 is equal to under root 1 minus n2 square upon n1 square. So we are substituting for sine theta 1 from equation 1. So we have sine theta naught into n1 by n naught under root 1 minus n2 square by n1 square. So as the fiber is in air, so we have seen that the light ray enters the optical fiber from air, and we are considering the refractive index of air to be 1. We know that for air or vacuum, we are considering it approximately to be equal to 1. So for air, we are taking n naught is equal to 1. So we will substitute this condition also here. So now what happens? Sine theta naught will be equal to sine theta naught is equal to n1. Because we have taken n naught as 1, we will simply write here 1 minus n2 square upon n1 square power half. Or we can also write it as n1 into, take the LCM, n1 square minus n2 square upon n1 square power half. Simply taking the LCM. Now I'll write it separately. 1 for the numerator, n1 square minus n2 square power half. And in the denominator, we have n1 square power half. It simply becomes n1. And this n1 and n1 gets cancelled. So what we have now is simply n1 square minus n2 square power half. So what we are writing here is sine theta naught is equal to n1 square minus n2 square power half. So this equation is the equation for acceptance angle. So this theta naught, we are calling it as acceptance angle, and in some places or some books, we also denote it by theta A. You can also write it as sine theta A is equal to under root n1 square minus n2 square. You can also represent it like this. Now coming to numerical aperture. So the light gathering capacity of the fiber is expressed in terms of maximum acceptance angle, and it is called as numerical aperture. So this is the exact definition for numerical aperture. Numerical aperture talks about the light gathering capacity of the optical fiber, and it is expressed in terms of the acceptance angle. Now the light gathering capacity is proportional to the acceptance angle theta naught. So whenever we write numerical aperture, it can be represented by the sign of the acceptance angle. So when I have to write the numerical aperture, so numerical aperture is equal to sine theta A. Now we are going to express this numerical aperture in a different form in terms of refractive index. So according to the definition, what we have seen, Na is equal to sine theta naught, and sine theta naught is equal to under root n1 square minus n2 square power half. Now let delta be the fractional change in refractive index. Fractional change here means when we are comparing the ratio of the refractive index of the core with that of cladding. So refractive index of the core is n1. Refractive index of the cladding is n2. So we are defining delta, that is the fractional change in refractive index, as n1 minus n2 by n1. So this represents the fractional change in refractive index. So from here you can also write n1 minus n2, that is the difference in the refractive indices, as delta n1. So I'm just cross multiplying, we get n1 minus n2 is equal to delta n1. So now how do we write this equation 1? So in equation 1 we have sin theta is equal to n1 square minus n2 square power half. So here we are going to use the formula. When we have a square minus b square can be written as a plus b into a minus b. So now n1 square minus n2 square can be written as n1 minus n2 into n1 plus n2. We have n1 square minus n2 square power half. So inside the brackets, whatever we have, we are expanding and writing it as n1 minus n2 into n1 plus n2 power half. So this becomes equation 4. Now let us substitute 3 in 4. So 3 in 4 means we have n1 minus n2 is equal to delta n. So substituting what we are getting, numerical aperture, delta n1 into n1 plus n2 whole power half. Now if we are doing an approximation, when we have considered that the refractive index of the core is slightly greater than the refractive index of the cladding. And here we are making a small approximation, that is, if the refractive index of the core is almost equal to the refractive index of the cladding. So n1 is approximately equal to n2. So n1 plus n2 will be equal to 2n1. This is the approximation we are making. In case n1 is approximately equal to n2, so n1 plus n2. So for n2 also we substitute n1. So n1 plus n1 gives us 2n1. So let us substitute it here. So Na will be equal to what we have, delta n1 into 2n1. For n1 plus n2 we are substituting 2n1. This is whole power half. So we have delta n1 into n1 is n1 square into 2 whole power half. Or we will write the numerical before, so we can write 2 n1 square into delta power half. Because n1 square power half becomes n1, we can take it outside the root and write it as n1, and inside we can put only 2 delta power half. So that is how we are writing it as 2 n1 square delta power half as n1 into 2 delta power half. So from equation 5, what we understand here is the numerical aperture depends only on the refractive indices of core and cladding materials, and it is independent of the fiber dimensions. When we have discussed about the structure of the optical fiber, we have discussed about the dimensions of the core and the cladding. But what we are trying to understand here is the numerical aperture, means the maximum angle at which it has to be incident for the light to propagate. The entire light, if it has to propagate through the optical fiber, numerical aperture is very important, and it depends entirely on the refractive indices of the core and the cladding. So if you want to have more details regarding these derivations or further derivation, you can also refer to these books, Engineering Physics by Palaniswamy and Engineering Physics by Gaurav. Thank you. See you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.